So what we're going to do is estimate area under a curve. So you know before how we had functions, and we were looking at the instantaneous rate of change at a point. Okay, that was a slope. What we're going to find out and be working you through is kind of the inverse of that application that we found for derivatives, is looking at the area under a curve. Okay. Now, to do this, it might be tricky. Like, how do I find that exact area under a curve? If it was a shape like this, or a shape we knew, maybe a circle or something, we could do. But underneath a curve, that's going to be a little bit more difficult. Also, something with the title, finite sums. So we're adding up like 10. Okay, summing 10 things. Not infinite. There is that as well, but we're not going to be doing that. So we're not adding up an infinite number, just a finite number. Okay, so I just talked about this. We're looking at instantaneous rate of change, and then a lot of mathematicians said, well, what about area under a curve? So let's look at this example. I made it more of like an application. Suppose a car is traveling at 60 miles per hour for 2 hours. So we just pick it up. Obviously, we would have had to start at 0, but we pick it up 2 hours, at 60 miles per hour. It goes for 2 hours. And we could say that, right, 60 times 2, we could do that to get 120 miles total. Right, that would be the total distance. Yeah. But what if we looked at this graphically? So I look at it graphically. What happens is, there's the graph, 2 hours, 60 miles per hour the whole time. It makes a rectangle. So what I can actually do is just find the area of this rectangle, which would be 2 times 60. And again, we would get 120. So that right there kind of leads like, well, okay, if we could find that, it'd be helpful if we could find it for any velocity, not just a constant number. And if we can, that would be a huge application. Like, if we had a curve, speeding up, slowing down, could you find the area under that curve? And that would actually get the distance there. And we can. Now, to start off, we're going to use a certain method, and later we'll incorporate antiderivatives. All right, but for now, we're going to do this. So I say, what if it varied? Just like the green up here. Well, we can't. We don't have a formula for that. So here's what mathematicians decided. We're going to do rectangular approximation method. They said, basically, let's just make X number of rectangles. Okay, X number of rectangles to estimate the area of the curve. Right? I did what, about 5? I did about 5 rectangles. It's not bad, but it's not going to be too far off, right? Like, I'll at least get an approximation. Again, these aren't going to be exact. It's approximation. So they used rectangulars. It's approximating, and that's the method. There are 3 versions. I'll talk about that in a second. But the one thing I was going to say, well, what if I broke these in half and did 10 rectangles instead? Do you think it's going to be more accurate or less accurate? More accurate. You can take a look at the bottom. I did a different curve with 2 rectangles. Not that good. 4 rectangles. Okay. 8 rectangles getting pretty good. And then I jumped ahead to 64 rectangles. It is a big jump, but I want to show you. 64 rectangles, that's fairly accurate, right? Like, I don't know if you can see on your page, but it goes like just outside and below, like just slightly. Yeah. So really not bad. Definitely not perfect, but not bad. So I say down here, yes, as you get more rectangles, the closer your approximation will be. And actually, as you go to infinity, how do you say that? As you go to infinity, in other words, if we did the limit as n goes to infinity, where n is the number of rectangles, it would be exact. Because limit is what it just approaches. Now, back to the 3 methods. 3 methods. Left ram, right ram, and midpoint ram. We're going to abbreviate those as L, ram, R ram, and M ram. And I should even say ram is rectangular approximation method. Let me give you an example of how these would look and how they differ. But this one is using left endpoint for your rectangles, right endpoint, and a midpoint. So let me just. So let's just say I had this curve, and I was starting to make rectangles. If I was using left endpoint, let's say I'm starting here, left ram, I'd put a point on my curve. This would be the left side, the left height. Okay, the height from the left side. Okay, and then I could do another one. So then this would be the next point lining up there. The next one, well, these are starting to. So then the next one will be right here. Okay, that one will go. So sometimes it's above, sometimes it'll be below the actual curve. So this would be, I'll just put L. That would be left ram versus right. Let's see if I get a similar curve. Okay, so right would be I choose a point, and that's the right. It's on the curve, but that's the right height for the rectangle. So the next one I make maybe would be here, and that's again the right height of the rectangle. Down there. Does that help a little bit? Do you see how it differs there? Left. It's just left, kind of. I mean, they're both heights, and the height of the rectangle is the height. But you form your rectangle by a left height or a right. And then midpoint would just be. Let's see if I can. So that's right. Here's midpoint. So midpoint would be if that's the midpoint of my rectangle. So my rectangle would be like this. So that corresponds with halfway along the base of the rectangle. So the next one would be like here. It would be. Right. So there's 3 types. I don't think I really ever make you draw a picture, but I like to so that you can see it. And sometimes I just ask when I see students do that. Okay, I think that's it. Oh, the last thing I want to say, and then I'll take some questions, is these are sometimes called Riemann sums, based on the mathematician who really worked with them and discovered them. Riemann generally gets credit for developing them. So I'll probably say Ram more often, but Riemann is another way you could say these. Okay, any initial thoughts before we try some? Yeah. That is a great question. Wow. For now, what we're going to do, yes, they will be. So I don't know if you guys heard. She said, did these like base it? I'm going to call it base or like width of the rectangle. They'll be the same. Yes and no. Like yes, that's what we're going to do, but we're also going to see some actually tomorrow where they don't have to be. So, and I'll say this: I'm going to use a formula, and all the bases will be the same. Tomorrow, we'll just do rectangles, but they won't be the same size rectangles. But for now, yeah, they will be. All right, good question. So let's turn the page, and I'll just show you the setup of this one. We're just going to do MRAM on this one. This is left, midpoint, and right. This is x squared, t squared. We're going to do midpoint, and there's a diagram. Okay, so you can see like the curve, like right there. That's the midpoint of the rectangle, of the width or the base. All right, so you can still think of this in terms of like a car or something or a model. I'm really just concerned x squared if we can use the RAM approximation. So we're going to do, we'll end up doing all of these for a different problem. I just want to intro it now and just show you the setup. Okay, so here's what we're going to do: midpoint RAM. Now we're going to do 6 subintervals. If I want to write this down, that means rectangles. Subinterval is like what's the not the total interval, it's the smaller interval that you're breaking up into. That's just how many rectangles are there. Now we're going in 0 to 3, 3 hours, or just 0 to 3. And so here's 0. First thing to get is how long the width or the base is for each of these rectangles. Okay, they're all going to be the same. You can, there's 2, I'll tell you a formula, or you can just always think through it. 0 to 3, that's the length of 3. So I'm looking at the width, or I sometimes call it the base. So it's 0 to 3, that's the length of 3. And we're doing 6 rectangles. So I divide that by 6. So 1/2 is the length of each of these. I might write 0.5 because I might use that a little more here in a minute. Now, if you're looking for a formula, here, write this down. B minus A over N. Okay, where A and B are the interval. Like we've done that before, like average rate of change, A rock. So A, on the interval between A and B. So this would be like in the interval 0 to 3. And so B would be 3, A would be 0. So it would be 3 minus 0. And N is the number of rectangles, which would be 6. This formula will always work. Sometimes students just want to they don't remember that. They just want to say, oh, it's 3 divided by 6. Okay, so that's the setup. We got the base, and we just need the heights of the rectangles. Good so far? Pretty good? Yeah. So here's what I'm going to need, is I'm going to need what the point, like the x-coordinate is for all of these. All right, so how far along we go. So I either suggest you make the rectangles a little drawing, or you can just do a number line. I guess I don't need the y on that. So just do a number line like this. This will be sufficient. 0 to 3. And you're going to make rectangles along there every half, or every 0.5. So I'm just adding 0.5. Like this one will be 0.5, this one will be 1. Then 1.5, 2, and 2.5. I would do it on the grid up here, just kind of small. Normally I would make. You could call it 1/2 too. It's just I think it's going to work out a little better if I just use decimals for this one. Okay, so you'll do this every time, and then depending on what RAM you're doing, you're just going to look at these values. Or since we're doing midpoint RAM, we're going to need the midpoints. So here's the values I'm going to need in between 0 and 0.5, halfway. 0.25. Halfway between 0.5 and 1, 0.75. So now for the green, I'm really just adding 0.5. So the next one is 1.25, and then 1.75, and then 2.25, and 2.75. So if I was doing left and right RAM, I would only use the red. If I'm doing midpoint RAM, I need the midpoints. So I'm using the green. I'll put this in green. Okay. And now we're ready to do the rectangle. So I'm doing length times width, or base times height for all of them. I'm just going to say base times height. So each rectangle will have a base of 1/2, and then we got to figure out the height. So here we go. So the area under that curve, using midpoint RAM, let me just say, so this, I might just write it like this. Here's rectangle 1. By the way, in the future, I'm not going to do this much detail. You'll get used to it. I'm just showing you for the first one. First rectangle is very hard to see. It's right there. The base of all these is 1/2. Right, so I'm just doing this, base times height. Okay, so the height is going to be really at that midpoint, whatever it goes up to on the curve. So I got to look at the function and whatever y value I get to on that curve. Now to get the y value, it's just as simple as I plug in x. Right, to get the y, plug in x to get the y. So what I'm going to do is I'm plugging in the x value that I want into the function. So 0.25 squared. So it depends on the function. If it was x cubed, I would have 0.25 cubed. So whatever the function is, it depends on that. I want to write one note here. Sometimes people will write this as 1/2 times f of 0.25. So like they're saying plug in 0.25 into the function f, or in this case b, and then evaluate. So 0.25 squared. just in case you want. I might do that a little in the future. Okay, and we're just going to do that for every rectangle. So now it's just writing them all down. So again, this is the base, that's the height. Any thoughts? Good on it? Questions I can answer? So if you get that, then you're going to be good for pretty much most of this section. It's basically that. Okay, so rectangle 2, which is right here, is going to be, the base is half, and then the height is going to be 0.75 into my function. So 0.75 squared. Third rectangle, 1/2 the base times the height, 1.25 squared. I'm going to have to go down here. Plus the fourth rectangle, 1/2 times the, what is it?
Oh, that's
1.75 squared. That's a 2, by the way. 1.25. Okay, plus 1/2. This is the fifth rectangle, so I'm using 2.25 squared. Plus 1/2 times the last rectangle, 2.75 squared. Okay. Yes, at this point you would have to put it in your calculator. I do have students who like to write out all 6 of these. I actually do that. I'm not going to make you, but if you get the wrong answer, right, then I can't give you as much partial credit. So sometimes you might just want to write, okay, this, I put it in, I got this, plus this. For our purposes right now, just so I don't want to take too much time, is I'm just going to tell you you would get 8.9375, which actually, you could look down here. Look at that table in a minute. Okay. Now let me, what did I do here? There we go. So let me contrast that with left and right RAM. Okay, so let me show you. I have a table that you can look at, on your paper or over here. So you see, if I was doing left RAM, all the bases are still the same. I don't know why they put the second. Left or right, there's still a 1/2 in there. Okay. So then the height, if we were doing left rectangles, we would have done, the rectangle for the first one would have been here. It would have been at 0, the height. So we would have done 0 squared. And then the next rectangle, it would have been at 0.5, would have been the next rectangle. So we would have the height at 0.5. And they run 1/2. And then the next rectangle would have been the height at 1. And so they did 1 squared. So you're using all the ones in red, except not 3. Because that one is, you won't need it. It's at the very end of the rectangle. But for right RAM, you would use 3. But for the very first rectangle, you're using the height at 0.5 on the right side. So the very first one, you do not use 0. But you would use 3. So I just want to contrast how you make that little number line, or just, you don't have to, just know the values. Either way, and then you plug them in. Last thing before I see if there's any questions is I showed you, here's if you would have worked this out for 6 rectangles, but then as you go to 1,000, you see it's getting closer and closer to 9. So for small values of n, small number of rectangles, midpoint RAM is usually better, but it actually doesn't matter in the long run because as you get to smaller and smaller and more rectangles, it doesn't matter. Okay, they would both go to 9. If you did 1,000,000 rectangles, so they're both about 9. What can I answer on this one?
That's the answer.
8.93. Yeah, so we're doing a finite number. We're not doing even 10,000 would be finite, but we're not doing an infinite number of rectangles. So this is what we get. And you can see it actually would be 9, but we're getting close. Any other thoughts? Now I'm going to do another one in a minute that does left, right, and midpoint. But here's what I want to tell you at the bottom here. Here are the basic formulas with a little diagram of what they look like, just so you can see, okay, left goes to left endpoint, right goes to right. So here's what I'm going to do in the future. See how there's that 1/2 on each one? It's not a 1/2, but I'm going to factor it out. Okay, so in the future, I'm going to GCF to everyone. So that's where, here's rectangle 1, here's rectangle 2, you add them all up. But what's going to happen is they all have the same base. And so it's going to factor it out. Same on this one, and this is just a funny way of saying the midpoint. So this is the y value at the midpoint. Okay. We're going to do left, right, and midpoint on the next page. We're going to do an example of that. Can I answer anything else, though? Okay, let's do one. So this is going to be x cubed minus 3x plus 5. Estimate the area of the curve using each version of RAM. And we're going from 3 to 9. Now, let me give you a brief sketch. X cubed, that's plus 5. So something like that. Let's just, here's 3, maybe here's 9. Rough estimate. Okay, it's x cubed plus 5. This would be 5. A rough estimate will look like that. So here's what we're really finding. We're estimating the area under this curve from 3 to 9. And so we're going to use 3 rectangles. Sub-intervals, rectangles. Okay, and each version. So I'll start with left RAM this time. Now I'm going to do, well, my little number line, I'll do it on here this time. So we're going 3 to 9. So that's 6 for the entire line. I divide it by the number of rectangles, which is 3, and I get a length of, or a width, a base of 2. And so I just need to go 2 to the right from 3, and I'll be at 5. 2 to the right from 5, and I'll be at 7. And again, you could have done b minus a over n, which would have been 9 minus 3 over 3. Because a and b are 3 and 9. So it would be 6 over 3, which is 6. Okay, so here's a quick illustration of what this one would look like for left RAM. I would go to 3 and use the left endpoint for height. The next one I use right here, starting at 5. And the next one will be right there at 7. I just make heights there. Again, you don't have to have that. I'm just showing you what it looks like. Okay. So base times height plus base times height plus base times height, but all of the bases are 2. So you'll see me in the future factor that out, which I'm going to do with this one. Also, I have students who sometimes don't like to factor it out. That's fine. It's just a little more work when you enter it into your calculator, but you're allowed to do 2 times the next first rectangle plus 2. Okay, you can do that. Just this is a little shorter. Okay, now I'm doing, I got 3 rectangles, left RAM. So I need the height. Here's going to be the height for my first rectangle. It's the y value at 3. Right? When x is 3, it's the height, the y value. So I'm going to need the y value at 3. I'm going to put in, on this one, f of 3 for now. So it means I'm going to put in 3 here in a minute. Okay, plus the next rectangle, I need the height on the left side, so it's the height at 5, f of 5, plus the next one will be the height at 7, and so it's f of 7. The reason I did it like that is because we're just going to plug these numbers in. I don't want to make it too cluttered. By the way, make sure you have a calculator out. It'd be good for you to try these. I mean, I'll do them on the board, but it'd be good for you to try these as we go along and just check. So f of 3, I'm just plugging 3 the entire function. So 3 cubed minus 3 times 3 plus 5. So it would be 27 minus 9 plus 5. So 23. 7 to 23. And some of these, I mean, I'm even looking at 7 here in a minute. You definitely need it. Just the numbers get high sometimes. So f of 5. 5 cubed minus 3 times 5, 15 plus 5. So I got 115. It's 125 minus 15, 110 plus 5. Okay, plus f of 7. So when I plug in 7, 327. Oh. Sum them, times it by 2, and that's it. You can write what you get, or you like 2 times, or just put them all together. So I got 930. You get that? Okay. All right. I'd like to contrast that with right RAM. Like you're going to see how similar it is. Very, very similar. Good on that? You're not going to answer? Oh. Why has it been doing this? Wow, that is frustrating. It's just the smart board.
Oh, and it's recording.
Yes.
We're on air.
But it's still recording. It's just the. I know. I had a great picture and everything.
How are you feeling?
It's not interview time. Okay, so it was something like this, right?
Yeah.
Okay. So now we're on the right RAM. So yeah, thank you, 5 and 7. All right, so the bases are still 2. 2 times height, 2 times height. Factor that out. Now here's a drawing of what would happen this time, just so you know. The rectangle here, I'd use the height at 5. So I go to 5, go up, make the rectangle. 7, go up, make a rectangle. 9, go up, make a rectangle. That's what it would look like. So I'm using the height this time at 5 for my first rectangle. Right, not 3. This time it's a height. Blue rectangle at 5. Plus the next one, the height's going to be at 7. And plus the next one, the height is at 9. So right now, even looking, I mean, it's not on the board, but even looking from what you have on the paper, do you see how there's only one minor difference? Like, that's the same, that's the same, that's the same, right? That's it.
Yeah.
That's the only thing, that's the only difference in right RAM. Because instead of using 3, 5, and 7 left heights, you use 5, 7. So it actually, sometimes it seems like a lot of work, but you repeat most of it for this one and a little for the next. So this one we already did. It was 115. 7 was 327. And if you plug in 9, 707. Okay, and I got 2298.
That's a very big difference.
It is. Well, why do you think that is the case?
Because you have 9 instead of 7.
Yeah, and x cubed, well, 2 reasons I can think of. One is x cubed goes up very quickly after even like 3 or 5, it's going up pretty quickly. What's the other reason? We're only using 3 rectangles, that's why. If we use 10 rectangles even, those numbers would be a lot closer, because they'd be a lot more, a lot smaller rectangle would be a little bit more accurate. So let's finish up with midpoint RAM for today. So this one, you got to do one extra thing. You got to find the midpoints of the rectangles. So 4, right? 3, 5, 6, and 8. Here, so I'll draw in green. To make the rectangle, you go up from the midpoint and make a rectangle. Up from the midpoint to the curve. Up from the midpoint to the curve. So midpoint RAM. Now, still have bases of 2, and now we'll just get heights at 4, 6, and 8. And so it's f of 4 plus f of 6 plus f of 8. And these are heights. You want to do 2 times whatever f of 4 is, 2 times f of 6. Let's see. So let me just give them 2. So I'm going to plug in 4, you get 57. Plug in 6, you get 203. And plug in 8, you get 493. And so overall, you get 1506. By the way, you can't, even though this one is mostly in the middle, you can never just do 24. You can't do an average. Okay. So you might think you just do an average of the left and right and skip midpoint. Well, no, it actually is going to be a little bit different. Okay. And that's where I was going to stop today. And we'll pick up with, I'll say a minute. I had a compass on there.
Do that.
You know what? I bet I was just doing compi and I wanted to show that. So anything I can answer with that for today? Now here's a preview of tomorrow. I'll do another example of this so we can see left, right, midpoint. But there's also two new things. There's table versions. This is where the base is not always the same. That's kind of what Brittany was asking. The base is not always the same. And one other thing I ask is, it's back on this one. Is I say, do you think rectangles are the only shape we could use?
Yes,
No,
of course.
you could also use triangles.
Well, I remember one time somebody said like circles, and I was like, well, I don't know how accurate that would be.
Triangles.
Triangles, yeah, like isosceles triangles maybe. Right.
This one this way and this one this way.
Well, but we just need one shape going across. So triangles, good idea.
Trapezoids.
Trapezoids
I suggested that.
actually work. Yeah, get that there.